All right. We'll get that. Okay, so we're going to talk about measuring theta over bar. So if we have experimental data, right, we can only measure the properties of the total mixture. But we ultimately want to be able to deduce how does every individual component behave in the system. Because the partial Gibbs free energy of a particular species is related to the equilibrium for the phases. So we'll need to have a way to figure out how component 1 is behaving in the system. Now we have a definition for theta over bar as dn theta under bar dni at constant temperature, pressure, and holding everything else constant. The downside is that it's not terribly convenient to work in units of moles, right? Because it adds an extra step of actually having to figure out, well, how many moles of every species is there in there. What's a lot more convenient in the laboratory is if you prepare a vial at a particular mass ratio or a particular mole ratio. In general, everything you do in the laboratory, you do it on a mass basis, unless you're doing volume basis for some sort of chemistry thing. But most all solutions you'll prep in the lab, you'll do it on a mass basis, then you'll convert it to a molar basis, and then you'll put it in some sort of an instrument. So what the homework is talking about is the change in volume. So typically what you would do then is mix up a solution at a particular mass ratio, calculate what its molar ratio is, put it in the densitometer, and it spits out a number for the density. And then the goal then is to convert from the density of the mixture to the partial molar volumes of all the individual species. That's essentially what homework 3 is. So if we take a look again at a binary mixture, in this case we can just say it's the volume of the mixture. This point right here will have to be the specific volume of component 1, which is only going to be a function of temperature and pressure. And down here, this is the specific volume of 2, which is the pure species properties, so it's only a function of temperature and pressure. But the total properties are a function of temperature, pressure, and decomposition. An ideal mixture is one where there is no change in volume upon mixing. So if I add 1 liter of component 1 and 1 liter of component 2, I get 2 liters. So in an ideal mixture, the volume over bar of I is equal to the volume under bar of I. So how the fluid behaves in the mixture is exactly the same as how it behaves in pure species. So then if we were to look at what the mixing may look like, last time we drew it as positive, this time we draw it as negative. Right, your mixture may gain volume or may lose volume. Right, volume is not a conserved quantity. Mass and energy are the only 2 conserved quantities. So as long as this system satisfies the first and second laws, as long as and mass balances, right, it's totally okay. So anything else that's not mass and energy is not necessarily conserved. So in this case here, this would be the delta mix of the volume at whatever that particular composition was at that particular temperature and pressure. So what we're trying to figure out then is how do we come up with who's responsible for this? Right? Is it component 1? Is it component 2? Which is the one that is actually causing this change to occur? Now, there are some theories that require this from a conceptual perspective. It's kind of nice to know which species is the one behaving more non-ideally. But when it comes to phase equilibrium, right? This is where it's really important to break down which of the species is having the particular properties, because that makes the phase transitions able to calculate it. Okay, so what we need. So all we should need is theta under bar of 1, and theta under bar of 2. We're only going to do this for a binary mixture. And the theta under bar of the mixture as a function of the composition. Now remember, these are going to be a function of only temperature and pressure. They're the pure species. And this is going to be a function of the temperature, pressure, and composition. Now, as a refresher on the definitions, so the delta mixing we can write it as the the mixtures property. Minus the ideal mixture scenario. Property of the mixture is written as the summation of the weighted average of the partial molar properties. And so we can write these together, and that the change upon mixing is merely the difference between the partial and pure species properties. So we can see that if any compound, or let's say all the compounds in the system, behave exactly the same in the mixture, right, which is the theta over bar, as they do as pure species, then we know that everything's okay and it's an ideal mixture. But if any one of the components in the system behaves at all different when it's in a mixture versus as a pure species, then we have a, basically a non-ideal mixture, and we will have some property change upon mixing of the system. So this is basically what we would do if we were running a particular experiment. For calorimetry, right, we would be mixing two components together, and we would see how much energy is released or absorbed by the system if it's exothermic or endothermic. Now, in the case of density, right, we have a very nice, convenient way to just measure the pure component properties or even look it up. So with enthalpy, for example, we would just say that the reference states are pure species 1 at temperature and pressure, pure species 2 at temperature and pressure. And we will be measuring the enthalpy of the system as it's mixed. So the question is, right, how do we use this information here to figure out what is theta over bar for each of the two species? Again, we are teaching the system. So all these derivations seem absolutely ever so convenient because they've been worked out in a way that makes it so they're nice and convenient. So what we're going to do is we are going to manipulate these expressions and the first one we're going to take is just the partial derivative of the delta mixing with respect to x of 1. In this case, it'll be a binary mixture. So all I've done is substitute in our expression for the delta of mixing right here. So for practice, we're going to do this derivation sort of in a dummy way. We're just going to take the derivative of everything. And then after the fact, we'll work out why some things cancel out. Good practice in thermodynamics because everything is a function of everything in thermodynamics. So we'll just do the derivation out in a very long form. And so we're going to have to do the product rule twice, once here and once there. Okay, so the derivative of the first times by the second. So x1 dx1, that's just 1. So we have theta over bar of 1 minus theta under bar of 1, plus the second times the derivative of first, plus x1 times d theta over bar of 1 dx1. Plus, we should get the same expression for no, we don't actually get a slightly different expression. I think I got that right. Okay, what can we cancel? Shout out to things we can cancel out. What goes away? What goes to 0 here? Give me two things that go to 0. What's that?
Theta 2 minus theta 2.
Yeah, this expression here? No, so that stays. So that's because right now we're going to assume this is a non-ideal mixture. So the theta over bar should not equal theta under bar. Over bar or under bar? Nope, that one stays. Yep, because I cannot, so that is this one here, so this one has to stay as well, right? Because I cannot change the mixture behavior of component. So if I change the composition of component 1, I have to change the composition of component 2, which means I'm changing the behavior of component 2. So this one has to stay also. Let me guys, there is, how many things cancel out? About like 4 things cancel out here. You're referring to this expression here. So that does not go to 0, but we can simplify that. So let's simplify this one here. So if we write out x1 plus x2 is equal to 1, then we can write out x2 is equal to 1 minus x1, and then we have this in a form where we can say that dx2 dx1 is equal to minus 1. So we can rewrite this expression here as minus 1. So that's one simplification we've got down. So give me something we can cancel out. So this is non-ideal, so the theta over bar does not cancel with the theta under bar. Yes?
The under bars don't change when you change the components because that's the ideal mixture?
No, okay, so you're on the right track, but it's because it's a pure property. So it makes no sense that the pure species property will ever change based on the mixture, right? Because it's not a function of the composition. It's just the pure species property. So these two terms are both 0. As a function of temperature, those terms, right, those would not be 0. But as a function of composition, it just doesn't make any sense, right? The pure species property of component 1 has no relationship to anything related to composition. So there's no functionality there. So if you thought about it as a mathematical function, right, there is no x term there, so it's just a kind of a constant, right? It would just go away. Now the next one's kind of tricky, but it goes back to the Gibbs-Duhem equation. This and this, that is the Gibbs-Duhem equation. x1 times d theta over bar 1 dx1 plus x2 d theta over bar 2 dx1. This is equal to 0 from the Gibbs-Duhem. Yes?
Why did the second d theta 2 dx1?
The underbar?
Yeah.
So same reason as for this one here. So in this case, for this term and for this term.
But wouldn't it have to be dx2? Because ideal mixtures don't change at all no matter what composition.
So as a reminder, so this term here, theta underbar of 2, this is pure 2 property. So the property of pure component 2, let's say this is a water ethanol mixture, right? So I have pure water and I measure the density of water, and I have pure ethanol and I measure the density of ethanol. That's not a function of any sort of mixture scenario. It's only a function of temperature and pressure. So if we were to write this out as some sort of a magic function, there's going to be no compositional terms there. Okay, so this simplifies down very nicely to d delta mix of theta dx1 at constant temperature and pressure is equal to just theta over bar of 1 minus theta under bar of 1. So this looks super familiar to what we kind of already started with. The only difference, though, right, is that in the delta mixing, right, it was the summation of x of I times by theta over bar minus theta under bar. So we're just missing that xi. So what we're going to do is very cleverly, we're going to evaluate the function delta mixing theta under bar minus x1 d delta which is going to simplify down to just theta over bar of 2, which is a function of temperature, pressure, and composition, minus theta under bar of 2. And that is our final result. So hopefully it makes sense that this term will cancel out because we're timesing it by the x1, and it looks just like the delta mixing term. So in our system now, right, we're saying that if we know the properties of basically the mixture, for example, let's say we're taking the density, we can very simply do a material balance to convert from density to a molar volume term if we know the composition, right? And so we can calculate the delta of mixing just based on the difference between the ideal properties and the real properties. We prepared our own solution, so we know what x1 is. We can somehow take the derivative of the data, and we know what our pure material properties are, so we can solve for this. So now we will have an equation for the overbar properties in our system. And of course, we can do exactly the same procedure for theta over bar of 1, but we just have to basically flip the x's and things like that. But the other trick here is that dx2 over dx1 is equal to -1. So the other option too is that once we've evaluated this integral right here, this derivative, we can just say that dx1 is equal to minus dx2. So we can be a little bit clever about our math and don't have to reevaluate everything completely. So if we're reevaluating this expression, instead of calculating theta over bar of 2, we want to calculate theta over bar of 1. Right? This is a totally symmetric system. It's totally arbitrary that we started with 1 versus 2, so we just swap all the numbers out. But the problem is, then we would have to evaluate d delta mix of theta under bar over dx2. You're going to have to do this numerically anyway. So once you've done it, right, we don't have to actually reevaluate this function. We can just take the negative of the one that we already calculated. If that makes sense. Any questions on that? Just some math tricks that save us a bit of time. Okay, so let's take a look at if we were to do this for real, like on a homework problem. So going back, one other thing here. So one thing that's really important to recognize here is that this is a very important term here. Basically, the whole foundation of partial molar properties is how does the property of the total system change when I slightly alter its composition or slightly alter the total number of moles of, let's say, component 1 or component 2. So what's really important is not necessarily so much what the actual property is, but how does it change when I move material, let's say, from one phase to the other phase. If we're trying to calculate vapor-liquid equilibrium for multiple components, right, what we're trying to figure out is, if I have one molecule going from the liquid to the vapor, I'm changing the properties of the liquid and I'm changing the properties of the vapor. Now, all equilibrium in thermodynamics is a dynamic process. So what we need to make sure is that those balance out, so that changing the composition really is nicely balanced. So the slope of how things change is really the important parameter to look at here. So that introduces some complications when we're dealing with real systems with real error in measurements. So if we were to draw out the delta mixing volume, for example, of some system, let's call it 1 and 2. So this is x1. So down here we have x2 is equal to 1, and up here we have x2 is equal to 0. I'm going to anchor this at 0 here, right? Because I can have no volume change of mixing if it's a pure species. And let's just say, for example, we have measurements that look like this. Doesn't look too bad. I mean, there's maybe a couple data points that are a little bit off. But let's say we kind of look at one particular area here, from here to here. If we wanted to evaluate the expression that we derived on the previous slide, we have to numerically take the derivative of this. And numerically taking derivatives of things is generally a very bad idea. Because if we were to evaluate the derivative here, it is positive. If we were to evaluate the derivative there, it is negative. Likewise, if we were to look at this section here, we have effectively a discontinuity in our slope, which means that as we try and evaluate this derivative here, it's not going to be a very smooth function. It's going to jump from positive to negative to positive to negative. Right? So that partial molar property is going to go all over the map. So instead, the ideal thing to do anytime we are dealing with real data, especially when you have to take a derivative of it, is you want to fit it to a function. If we fit it to a nice, smooth, and continuous function, then we're in good shape. thermodynamics is exceptionally fickle to inflection points, changes in slopes, and so there's a certain series of polynomials that are very useful to use in thermodynamics, whereas just sort of, if you're looking at Excel, you're right-clicking, you say, oh, add a tread line, and oh, linear doesn't work. I'm going to go second order. Oh, second order doesn't work. I'm going to go to polynomial. Let's do a cubic one. Oh, that one doesn't work. That does not work for thermodynamics. Let's say, for example, we just have a little teeny inflection point there, and you chose a cubic polynomial. That could cause big problems, right? Because the curvature of the functions are exceptionally important. Just like how we built the entire foundation of vapor-liquid equilibrium using a cubic equation of state, the entire premise of that is built on the curvature and not allowed roots based on entropy stability. So you have to be extremely careful of a couple of things in thermodynamics. One, that your 0 points here are actually 0. Because one of the most important properties that we can look at is the infinite dilution partial molar properties. So if I take 1 drop of ethanol in a sea of water, it's going to be extremely unhappy, right? And it's a way that we can gain insight on how ethanol and water behave with one another. Because effectively, you're isolating a single ethanol molecule around a sea of water. And so it's definitely going to behave in a manner where it really doesn't like to be around there. So when you look at your partial molar properties, they will have a couple of key characteristics. So if I were to plot out, and I don't know if this is necessarily representative of the data that we're looking at here, the partial molar volume of, let's say, species 1 in the system. Okay? So down here, there is no x1, and up here it is pure x1. So for pure x1, what does the partial molar volume have to equal to? The ideal molar volume, yeah. So we'll just set this here as, say, B of 1. Right? It'll have to be something like that. But on the other end, it doesn't have to. It can be high, it can be low, it can be all sorts of different things. Right, so you have this limiting case where as pure systems occur, you have to equal 0. The delta V of mixing or the delta theta of mixing has to be 0. But on the infinite dilution point, the infinite dilution, that is not necessarily going to be 0. And so you've got a lot of weird characteristics. And some of the goals of thermodynamic measurements is, can we just measure the infinite dilution volume and then basically predict all the properties of the rest of the system? Saves everyone a lot of time. So the strategy to this is we fit it with a very specific type of polynomial. Now there are a lot of options to choose from, but one of the most popular ones is called the Redlich-Kister form of a polynomial. So this polynomial has a lot of good characteristics. The main one is that if I have either x1 or x2 is equal to 0, then the delta mixing has to be equal to 0. Now, none of these are fail-proof necessarily, but matching that property is really important. So in the homework, you're going to have to fit real data with a Redlich-Kister polynomial, and then take the derivative of it, and then calculate the partial molar properties. But the thing to remember is if we go back and we take a look at our function here, which has been doodled all over, but basically we have to evaluate this as a function of dx1. So we have to do a little bit of numerical substitution or algebraic substitution to get this entire function into a form only as a function of x1. Or we can do the approach like we did when we started the derivative, right, where we calculated things as everything's a function of everything, and then we just substituted out, dx2 for minus dx1. But you'll have to numerically evaluate this function here. And then you'll fit these coefficients of your polynomials, and this is the order of your fit. So you can have a second order polynomial, third order polynomial, fourth order, so on and so forth. But the key thing with a lot of thermodynamic data is that inflection points may carry along with it a lot of different valuable information. So one strategy, and I'll talk really briefly about a strategy that we can use to actually fit the data. So let's say we've got some function here that we're trying to fit. Right, that's our ideal polynomial. But it's never going to hit all the data perfectly, right? So what we want to know is how do we numerically benchmark one fit of a polynomial as better than another fit of a polynomial? One very common approach is to calculate the sum squared error. This is my default. This is effectively kind of like what a least squares does, right? It measures the deviation between the fit and the real data, and it squares it. So what you're really doing is you're minimizing the area of squares whose length is the difference. So if we were to do this in a spreadsheet, we would have, let's say, x, and then we would have delta v of mixing. Then we would have delta v of mixing calculated, right? And this would be based on our polynomial. And then we could do the difference squared. And at the bottom, we would sum it all up. So if we were to do this in a spreadsheet. So we can add 0, 0.1, 0.2, so on and so forth, to 1. Now at 0, the difference should hopefully be 0, right? Because your polynomial is designed to be exactly correct at the endpoints. So effectively what we'll be doing then is calculating the difference between your prediction and the real data, and then squaring it. So that's kind of like just making little boxes here. This is exactly the same concept behind least squares. But with least squares, you can analytically solve for what is the best fit. But in this case here, if we're doing this numerically, we're going to have some spreadsheet table of our coefficients. Let's use the same nomenclature for our system. A of 1 and A of 2. You're going to have to fill in some initial guesses. That'll be used to calculate this here. And then you take the difference of, this is delta V1, delta V calc 1. So you would have delta V1 minus delta V1 calculated squared. Then in Excel's solver, or MATLAB has curve fitting as well, your goal is you basically say, okay, I want to minimize this by changing these cells. And you may have to tune your initial guesses and things like that a bit and play around with it. But ultimately, that's what you should be able to do to curve fit the polynomial function. Okay, any questions? Yeah.
So then the first delta V mix, is that the ideal ones?
So that should be 0 also. If your calculations are going right.
Oh.
That should all be 0, right? Because you can't have a volume change of mixing if there's no mixing going on. Same thing has out of the limiting properties of the partial values should always decay back down to the pure species values. And this should hopefully be 0 as well. And same thing down here. All right, so you're minimizing the squared deviation between your predicted values, which is from your Redlich-Kister polynomial, to your actual experimental measurements. And the whole point of this is that you want to smooth out any uncertainty, because when you take numerical derivatives, you exacerbate experimental uncertainty. When you numerically integrate, you smooth things out. That's quite nice. So numerically integrating is no problem at all. Numerical differentiation is a big problem. Okay, so in terms of all of the heavy lifting of new terminology, basically we're done. We've gone all the way from the fundamental principles of the first and second laws of thermodynamics all the way up through the foundation of multi-component and multi-phase. There are a few lingering terms that we need to define, like activity for chemical reaction engineering or chemical reaction equilibrium, and excess properties. But apart from that, this is it, right? Or an activity coefficient and things like that. But these are all just more convenience functions that help us simplify and solve problems. So now it's going to be starting off obviously with the ideal gas law. Let's take these expressions we've derived, let's substitute in the ideal gas law, manipulate it and see what we get for partial molar volumes and all these different partial energies and things like that. And then eventually we'll work our way up to liquids and we'll realize liquids are really hard. So it's kind of annoying that we spent all this time doing this very detailed and rigorous derivation of thermodynamics, but then we run into the roadblock of, oh, we don't have a function that is accurate enough to actually apply these theories. And liquids is that one big pitfall. We don't have any good equations of state that can predict the properties of liquid mixtures well at all. At least nothing that's very trivial. We have some good correlative ones that have studied so much data that they kind of derive some general rules. But that's where the activity coefficient comes in. The activity coefficient just says, okay, we can't predict this, but we've got a pretty good system for organizing data. So we're going to use this activity coefficient as a way to condense really complex concepts down to a very simple parameter. And so now it's all going to be about simplifying our systems down to where we can actually either tabulate simplified stored data or calculate information directly from an equation itself. So what we're going to do now, with a little bit left, is we're going to start talking about ideal gases. So in the book, the Sandler book, we have gone up through chapter 8 and we have finished chapter 8. So now we're starting on chapter 9 and we're like, what, 4 weeks into the semester, 3 weeks in? So we're going at a pretty rapid pace. And it's not a small book either. I mean, 8 chapters is no slouch. So on chapter 9 is what we're talking about as ideal gas mixtures. So the ideal gas, PV equals nRT. Now that we're dealing with multi-component systems, I'm not going to switch it and abbreviate it as PV underbar equals RT, because we can have lots of different contributions from different molar species. And we can write N is equal to the summation of all of the individual constituents of the system. Now, the entire premise of an ideal gas is that the molecules are so far apart that there is no way that they can feel the presence of any other molecule, regardless of if it's the same type or if it's a different type. Okay, so then we can use that premise to come up with an expression for what we think that the internal energy of an ideal gas mixture, IgM, this is going to be a function of the temperature and the number of moles in the system, the total number, right? Because this could be any arbitrary amount of Ni, Nj, so on and so forth, right? We know already, right, that the ideal gas energy is not a function of pressure or specific volume, right? Because if you're infinitely far apart from your next neighbor, or effectively infinitely far apart, by half that distance, still infinitely far apart. You're still not feeling the presence of them. So we theoretically should not expect that an ideal gas will behave at all by changing the density or the pressure, only the temperature, which controls the internal organization of that particular molecule and its velocity. So I'm going to say that this is just equal to n j u underbar j. Right? I'm just adding up the individual contributions. So this is effectively, I'm writing out a model for how I think that the ideal gas mixture should behave. And it makes sense on a theoretical or conceptual basis. So now what we're going to do is we're going to take this information and we're going to plug it into our definition of the partial molar properties so we can derive what we think the partial molar U is at. So U over bar of I, that tells us what is the properties of I in the mixture for its internal energy. In an ideal gas mixture, we're going to be general here. We're going to say it's a function of temperature and potentially the composition. Now our definition of the partial molar property is that how does the total internal energy of the system change as I add a little bit of species I back into the system. And so we are going to substitute in our model that we wrote and derived and see how we should expect it to behave mathematically. So this is equal to d dni of the summation of n j u underbar j. And so now it makes sense why I changed the subscripts around. So in this term right here, what should cancel out? This is an arbitrary summation. So if we were to write this out, we could say that this is dn of, let's say, I don't know, 1 dn 1 u underbar 1 plus dn 2 dn 1 u underbar of 2, so on and so forth. How would I simplify this expression? Because in multi-component systems, we are going to have to deal with these long derivations, long summations, and taking derivatives of them. So in this expression that I drew up there in blue, what can I cancel out? What goes away? How do I simplify this? First term, what happens to the first term? This just goes, so this here cancels out and goes to 1. Okay, and then what else? What else can I cancel out here? Correct. The number of moles of 2 in the system is not a function of the number of moles of 1 in the system. Now, this is not the mole fraction. x2 is definitely a function of x1. But in this case, the total number of moles is not a function of the other one. So from this, every term in this expression here is going to go to 0, except for the very first one. Or whatever, in whatever cases, if I is equal to j, that is the only time we get a non-zero system. So mathematically, we get the conclusion that we were hoping for. This is for an ideal gas mixture. IgM. That the internal energy of species I in the mixture is exactly the same as the internal energy of species I when it's on its own, because it doesn't know that anything has changed. And mathematically, it all works out great. We've taken our derivation of the partial molar properties, we've substituted in our model for what we think the energy should behave like, and it simplifies down to basically what we would anticipate it should be. So we won't be able to get to entropy today, but we can cover volume and pressure. Okay, so we're going to take the same approach with V over bar of I. So we're going to calculate what V over bar of I in an ideal gas mixture is. So I'm just drawing in these parentheses for functional form just to remind us that this is the mixture properties that we're dealing with. But at some point I may truncate that a little bit. But just remember, everything's a function of everything. But since it's the new nomenclature, the over bar, right, is a function of the total mixture property. So I'm still kind of writing that out a bit. So we can write this as dV of an ideal gas mixture at constant temperature, pressure, and also all the business about all the other n's being held constant. So we can write this then as dDNI at constant temperature and pressure as the summation of NJRT over P. All right, so we've just substituted in the ideal gas law, PV equals nRT, but I've just solved for V and substituted it in. Same exact process. Everything goes to 0 except for when I is equal to J. So V over bar of I is just equal to RT over P, which is equal to V over N of I, which is V under bar of I. H is defined as U plus PV, so we can just say that H over bar of I is equal to H under bar of I as well. Right, because remember, the partial molar properties are at constant pressure. So this P here doesn't factor into it because it's constant. This is based on how we formulated the partial properties. And the last definition that we'll cover, this one is strictly a definition, just for convenience. So we're going to call P of I as the partial pressure. And this is equal to X of I times by P, which is the total pressure. And you can work it out to show that the partial pressure is the pressure that species I would exhibit onto the surroundings if it were the only thing around. But the partial pressure is really only a concept that you can apply when you have an ideal gas mixture. If you have a real fluid mixture, then the pressure that species I exerts on the surroundings is going to be influenced by its local environment of, what is the composition around it. If there's a net attraction of the gas to the molecules, then there's going to be a lower pressure. If there's a net repulsion, it's going to be a higher pressure. But the partial pressure as a concept is really only applicable to ideal gas mixtures. But for chemical reaction equilibrium calculations, in general, we tend to assume it's an ideal gas mixture, at least for most of the calculations. They can get pretty hairy if you don't. So this is where partial pressure really comes into common a lot, is because a lot of the reaction problems that we'll do and that you may have done in the past, they're mostly all based on ideal gas systems. Okay, so on Monday, we are going to hit entropy of mixing, and that's going to transition us into another definition of excess properties, because the entropy of mixing is not pleasant. Even the best case scenario, there's discontinuities and infinite values and all sorts of unpleasantries. So entropy is sort of a thorn in our sides when we deal with this kind of stuff, which is partially an explanation for kind of the arbitrary definitions that we have for a lot of multi-component phase equilibrium calculations, is because entropy causes complications when you mix things together. Okay, have a good weekend and see you guys all on Monday.